Still can't believe we gotta do this over WebEx.
Okay, did it say it's being recorded? I didn't know if it was going to give the indication or not. It's recording now. Okay. All right.
I
I'm
don't
going
know.
to go ahead and start then. All right. So, hello, we are Team 3, and this is our conceptual design review of an autonomous pick and place robot. I'd like to introduce our team, our CAD team, Josh Lewis, Brian Sullivan, and Franklin Adubando. Our calculation team, Nick Sekulik. Our electrical team, Stephen Seck and myself, and our presentation and documentation specialist, Alex Stevenson. Here is an overview design of our pick and place robot. The yellow subsystem represents the base, which would include the feet. The red is the RA1 system. The blue is our rotary axis 2. The green is rotary axis 3. And the pink is the gripper subsystem. And I will hand this off to Brian.
Hey everybody, I'm Brian Sullivan and I designed the base and supporting components, and Nick performed the calculations. Here are a couple more views of the base. You can see S1, S2, and S3 respectively. Then you can also see on the bottom we have our motor for RA1 mounted, as well as some adjustable feet, and you can see the holes for S1 and S3. We also already have most of our mounting holes for the Arduino and other supporting components that we will add fasteners to later. Here's an overview, or an over-top view of the base, where you can see the Arduino Mega power supply are mounted, as well as RA1. There is a small gear attached to the RA1 motor that drives the red gear, which is the bottom of RA1. S3 is over there to the left, and S1 is to the right, and you can see there's some little chamfers on those holes to better support and guide the balls through, the metal spheres through the holes. The toggle switch will be used to switch from manual and autonomous mode. Here are the adjustable feet. They are made of steel and have universal threading on them. They can be used with any tap that you would find in a typical machine shop. They're adjustable in height individually up to and from 0 to 20 millimeters, and they can be locked into place with a nut. Here's some dimensions of the base, with the 0 point of our coordinate system in XY being the bottom left corner. All these dimensions are in millimeters, and we also have listed a position of RA1's center, which is 172x and 100 millimeters in the Y direction. We've provided the base height, S1, S2, and S3 depths and widths, which are all listed here. Guys, I haven't studied this one yet, so I'm going to free ball it, but later on, tomorrow when we go through it, I'm going to be better. Okay, so basically we modeled the base as a beam here, and you can see distributed loads for the respective weights, and we have a moment where the force of the arm and basic robot component of RA1, 2, and 3 in the gripper are there where it says F arm and the moment of the arm. We also have provided coordinate systems for these as well. Then we have the symbols and the actual components. So this is basically just where we have the component and its symbol matched up for further description of the calculation. Here are two shear diagrams of the X and Y directions with respect to position. And here are moment diagrams with respect to position for X and Y as well. Here is an X and Y with respect to position graph of the deflection of the base, where your yellow and orange are the lowest deflection starting at 0, and the blue sections are the maximum deflection, which is in the middle. Here's a moment diagram of the base in the X direction with respect to position. Here are some calculation values and equations. You have stress and torque. We have the max moment of the base, distance to the center, cross-section, the second moment of an area, cross-section width, shear force, and first moment of area of 1/2 of the cross-section, which is a cube. So there's some X and Y values over here in Newton meters, millimeters. Here are final calculation values for bending stress, shear stress, deflection in the X, Y, and total deflection in megapascals and millimeters, respectively. Here are some of the materials that we use to construct the base. The base plate is aluminum, and that is the 5 mm thick portion that is S2, which is also under S1 and S3. So both of those, or all of those sections have that aluminum base under it. Then the riser portion of S1 and S3 are made out of ABS plastic that is 3D printed with a 10% infill. And then the feet are made of steel. Here are our factor of safety calculations. Our factor of safety is 16 for the base. And I will now transition to Alex for rotary axis.
Thank you, Brian. My name is Alex Stevenson. I'm going to be talking about rotary axis 1. So as you can see here in red is rotary axis 1. It's going to consist of a riser, a lazy Susan bearing, and a gear system that will rotate the entire robotic arm up to 270 degrees. So the purpose, like I said, is going to rotate the entire robotic arm so it can reach both S1 and S3 to pick up the spheres and move them. It has 270 degrees of freedom of movement going all the way clockwise or counterclockwise if you were to add the two. And the RA1 consists of a riser that is going to allow us to more accurately pick up the balls in S1. Allows for easier coding, and it also allows us to have clearance when we go to S3, moving the robotic arm and during that rotation. It consists of the riser, the stepper motor, and the lazy Susan bearing. So this is a couple of brief angles regarding RA1. As you can see here, the riser gives us a little bit of clearance so we can get to the elevated S3 portion. The stepper motor shown below, mounted to the bottom of the base plate, seems to be quite large here. In future iterations, it will be smaller as we have calculated the torque for that. The limit switch and tab that you can see here are used in the autonomous systems that will be talked about a little bit later, but are used to zero out the RA1 subsystem. And then the lazy Susan bearing, we can see here, the red portion is the gearing that is going to be connected to the stepper motor here. And it allows, it's got, I should have my thing ready. Brian, I'm not going to say this during the presentation, but that, what would be called the gear that's attached to the motor?
Just the RA1 gear. Oh, the driving gear, I guess.
Okay.
It's a pinion.
Okay, so the driving RA1 pinion has 9 teeth, and the gear in red there has 72 teeth. It is an 8-to-1 gear ratio. And as we can see further, the mounting bracket, which contains the lazy Susan bearing, that is press fit, and it's mounted to the base there. And so we can further go to the dimensions of RA1 with the height being 80 millimeters, and we can also see the cross-section dimensions there as well. And we go into calculations. The speed required that we wanted to get was 45 RPMs, giving us roughly 47 radians per second squared for the speed there. And then for torque, we calculated the maximum torque to be roughly 1.5 Newton meters to use in the motor attached to the base plate. The bending stress that was calculated was roughly 74 kilopascals. And the materials used, the mounting bracket would be steel, the lazy Susan bearing, the press fit bearing there would be steel, and the riser itself was aluminum. And then furthermore, we calculated the deflection, which was a compressible deflection due to the forces pushing down from the rest of the robotic arm. It was very minimal, only 7.6, 10 to the negative fifth millimeters, so pretty negligible there. And we did also have a factor of safety, which is extremely high, roughly 3,200, when we were focusing on getting a factor of safety on 10. And I will pass this off to Stephen.
All right, thank you, Alex. Hey, what's up, guys? My name is Steven. I will be presenting Rotary Axis 2. Here's an overview of Rotary Axis 2, where it is outlined by a red square box. All right, so RA2 is the first part of the robot's arm that is used for elevation change between S1 and S3 of the base. RA2 is also the first part of the arm that is chain driven and is mainly made up of the arm, the stepper motor, and the chain. Here's another overview of RA2 where you can clearly see how it is connected to RA1 with a pin and bearing connection. Like mentioned earlier, RA2 is driven by a chain made up of carbon steel. Here you can see where the red arrow is. That's the motor that's going to be driving the chain to move the whole arm. All right, so these are the dimensions of RA2, with the length being 180 millimeters, the cross-sectional area being 80.6 millimeters squared, and the diameter of the pin connecting RA2 to RA1 being 5 millimeters. And then these are the calculations of RA2, credits to Nick. So for speed, we ended up with 20 RPMs, which ends up converting to 20.9 radians per second. Here we found the torque we needed for the stepper motor to move the whole arm, which will be geared up. The torque ended up being 2.6649 Newton meters. Here is the stress we calculated, with the shear stress of the pin being 153.8 kPa and the bending stress of the whole beam being 6,665.4 kPa. Here is the shear diagram of RA2, with 0 being the position of the pin connecting RA2 to RA1 and 0.18 or 18 being the connection to RA3. Just like the shear diagram, this is the moment of the beam, with our maximum being negative 2.3 Newton meters. The arm and pin of RA2 is made up of aluminum, where the chain that we are using is made up of carbon steel. With everything we do calculate, we calculate with a factor of safety, and we end up with a 36 factor of safety for RA2. Here is the deflection of RA2, where we ended up getting a deflection of 0.02 millimeters at the end of the arm, which is MB. And here I will be passing it on to Josh.
Hey everybody, so my name is Josh Lewis. I will be presenting the Rotary Axis 3 due to Jordan's absence and the gripper basket. So the Rotary Axis 3 is labeled as the green section and highlighted by the red box in our overall diagram. Next slide, please. Our Rotary Axis 3 consists of the beam, the stepper motor, the chain and gear. It's just like Rotary Axis 2, used to rotate around to control where the ball was going to be picked up by the gripper. Next slide. Here are the views that go across to show a better angle of what is consisted of RA3 and what is attached to RA3. Next slide. As we stated before, these are all going to be rotated by a chain. So we're going to have a carbon steel chain, which will be able to act as a extra arm to connect between the two rotary axes to allow for a complete 360-degree rotation, minus the area that it comes in contact with the limit switch or any other components in its way. Next slide. Just like RA2, there will be driven by a stepper motor, which allows for accurate control of how far the arm will rotate, and it will allow for smooth and easy control of which location the arm is controlling towards. Excellent. These are the overall dimensions of the arm, similar to RA2, but a little bit shorter, just because we're looking for more finite placement of where we're trying to get the gripper to be located. Next slide. And we'll look at some of these calculations to prove why we chose what we did. Next slide. Similar or identical to RA2, we're going to be using 20 RPM, which allows for a smooth transition and not a crazy speed, but not too slow to be able to control the arm movement. Next slide. We calculated the overall torque that's going to be applied to the arm at 0.12 Newton meters to make sure that we have enough torque for the motor and for everything else required to make sure that the arm doesn't bend or break. Next slide. And speaking of braking, we have our internal stress. So just like RA2, it is connected to a pin, and that pin is going to be required at a stress of 121 kilopascals with the internal bending stress of the entire arm of 532.5 kilopascals. Next slide. Here's a diagram to prove that we have our arm shear stress. Next slide. And similar to the other graphs, we have a moment arm, which just shows how far we go up before we reach the other pin and connect it to the gripper. Next slide. Again, just like RA2, we have our materials. We have the arms made of aluminum and the chain made out of a carbon steel. Next slide. And because this is a little bit more of a finite portion that we consider failure to be a concern, we have a very high factor of safety, which greatly exceeds our minimum factor of safety of 10. And towards the end of the arm, we can expect a decent amount of deflection because of the gripper being pulled onto it, but not as much as the entire arm itself. And we need to take this into consideration due to the accuracy required to make sure that the gripper picks up the ball in the right location. Next slide.
I'll have to add that.
And we're going to be looking at the gripper assembly and the sensors attached to the gripper to make sure we have an accurate representation of where the balls will be. Next slide. Here's several images of the gripper assembly itself. Next slide. And it contains the basket itself, a magnet, a crank slider, an ultrasonic sensor to identify where the balls are located. The basket itself is going to be a little more complex than shown in the CAD diagram. The basket itself will be similar to a wire mesh, similar to having springs on the sides, which will allow to cradle the ball, but also be able to guide it for disconnect of magnet. Here's an animation of our crank slider mechanism. You can see that the crank moves throughout the entire basket, reaching below the exit of the basket to make sure we get clean contact with the ball, and rises just to the edge of the top of the basket to allow for an easy disconnect from the ball and the rest of the basket and crank slider. The magnet itself is a small cylinder inside the middle of the basket, which is able to move freely and has a small pin to allow for direct contact with the ball and easy rotation. The servo motor will be one of the actual Arduino motors that come in our kits, which will direct drive the crank around the flywheel portion. I guess it's not really a flywheel, but will be a direct line from the servo motor to the crank method to allow free rotation of the magnet and movement.
Oh,
The ultrasonic sensor will be downwards facing off the edge of the basket. This essentially allows us to identify how far away the ball is from the rest of the plate, which not only allows us to identify if there's a ball in that location, but allows us to be very accurately able to determine how far away we are to be able to pick up the ball freely with the magnet. And we had to do a couple different calculations to determine that the crank and slider would move without having any sort of contact or clipping through the edge of the basket, as well as making a smooth rotation of the arm to keep constant motion of the magnet to make sure that we don't have any jankiness that might drop the ball or cause any sort of interference. The gripper itself is going to be fairly lightweight because we don't want an awful ton of weight hanging on the end of our arms. We have a lot of ABS plastic inside the actual shell itself, but the crank and the crank arm will be made out of aluminum to make sure they're strong and sturdy and won't bend. And moving on to the calculations. As you can see here, there was sorry, what do I want to say here? My bad. We're going to be looking at the RPM and the overall torque applied to this crank and slider because we want to make sure that the torque or the RPM isn't a too crazy high number because we don't want it to be, again, spastastic where it's just moving really fast and causing the ball to be disconnecting from the magnet. And we also want to make sure that the torque on the edge of the crank is not too much or it might cause bending in the push rod system. with that smooth RPM, we can get a nice wave access of what is going to be happening with the end of the magnet, which allows us to easily identify how far away we are from the ball and where we are in our rotation section to figure out how far we need to move the crank to disconnect or connect to a ball. The bending stress on the end, this is where the connecting point is from the magnet, or not from the magnet, from the gripper assembly to the rotary axis. So as you can see, it's on a little pin and gear system similar for the stabilizing section, which has a little bit of stress on it, but not an awful ton. We have to worry about upgrading from the plastic to a metal shell. And because a lot of it's made out of plastic, we're going to make sure that there is going to be no failure of this. So we had to keep an eye on factor of safety, and the factor of safety of 40 greatly over exceeds our factor of safety requirements. And as I was stating before with the self-stabilization, we need to make sure that the gripper is always facing down to connect to the ball perpendicularly. So we have the torque required to move the gripper to make sure that there isn't any sort of slippage of the gears or anything to make sure that we can get the motor moving the gripper assembly evenly. And I'll be handing it off to Philip for the autonomous control.
All right, thank you, Josh. My name is Philip Brown again, and I'll be describing the autonomous control for our pick-and-place robot. Components that are utilized by the autonomous control are the Arduino control board, a toggle switch for switching between manual and autonomous mode, limit switches for zeroing our 3 stepper motors, a power supply, an accelerometer for stabilization, an ultrasonic sensor for sphere detection, wire connections, a laptop, and the code. Here is our 2560 Arduino Mega board that will run the code to operate the external systems. So our design utilizes 3 limit switches. We have a stepper motor that runs RA1, RA2, and RA3. At startup, the code uses the system and runs them in one direction to zero out RA1, RA3, and RA2 respectively, so we have a good starting point. Here is the stepper motor. This could be RA1, RA2, or RA3. They are all identical wiring diagrams, however they'd be connected to different pins on the Arduino Mega board. They all use a motor driver and an external power supply. We also have 2 servo motors. One servo motor operates the stabilization axis, and the other servo motor operates the crank slider mechanism. The servo motor that operates the stabilization unit has been modified to take away the location control and allow it to operate to go all the way clockwise or all the way counterclockwise continuously depending on the command. And the servo motor for the crank slider is a stock servo motor that will only go 180 degrees. Here is our accelerometer. It is mounted to the top of the crank slider and gripper mechanism and measures within a band to control the servo motor that actuates the stabilization axis to keep it within plus or minus 10 degrees of level. Here is our ultrasonic sensor. It is mounted to the side of the gripper and detects spheres on top of the S1 area. And I'll now pass it off to Franklin, who will cover the manual controls.
All right, so my name's Franklin, and I'll be covering manual control. So manual control basically includes the toggle switch, the wire connections, the Arduino board, and the code. So if you look closely over here, there's going to be a black pin on this breadboard. And that black pin is basically what toggles from what Philip was talking about to what I'm going to be speaking about, which is autonomous mode and manual mode. All right, so if you look over here, this is our controller. We went with a two joystick controller, which controls RA1, RA2, and RA3. All right, so these two joysticks are going to be connected to the Arduino. All right, now going into more detail about RA1 and RA2 and what the joysticks do. For more importantly, if you push down the button for the left joystick, it'll fully extend the gripper. Going up and down will move RA2, and side to side is a RA1 movement. So for the right joysticks, pushing down on the button fully retracts the gripper. And similarly, up and down is a stabilization motor, and side to side moves RA3. All right, so this is going to be the complete wiring diagram that we had. This is basically the overall subsystem of the autonomous and the manual control system. All right, so now I'm going to be moving over to Nick for uncertainty calculations.
Hey, my name's Nick. I'm going to be presenting uncertainty calculations. So as you can see on this top-down view of our base, we have all of the holes listed 1 through 22. We calculated the exact angles that we need for every single motor to hit all these positions accurately, depending on the height of the risers on the base. Next slide. And as you can see, with a gear ratio of 1 to 8 and a confidence of 95%, we calculated the uncertainty for every single hole. And next slide, please. We did this by using the equations in the top left corner of this slide, where we have X and Y coordinates for that plane we were just showing in the initial slide. And to do this, we utilized an uncertainty analysis, a standardized one, in which we did a first order Taylor series expansion of the uncertainty of each of these with respect to each variable, such as the angles, which are, which are influenced by the motor of choice, in which stepper motors have a uncertainty of roughly 1.8 degrees per step is what we used. And and for instance, also with the links have a standard deviation uncertainty. So for instance, 180 millimeters had a uncertainty of 1.8. And that's the values we used in these equations. And we calculated the uncertainties for all of them, as you've seen on the previous slide. And then we found the 4 worst uncertainties, and we have them listed below, hole number 1, 16, 19, and 22. And if you can go to the next slide. As you can see on here, this is where the positions are listed. And so the uncertainty is a little bit higher for the S1 holes. However, that's okay, because we found that the maximum uncertainty allowed in those holes is 4 millimeters for the S1 platform, and the maximum uncertainty allowed for S3 is 2.5 millimeters. So the values that we calculated were all in spec, and those are the holes with the highest uncertainty. And these are the references for some of the GradCAD and whatnot that we use. So, are there any questions?
Well, I got right at 28 minutes, so that's
Yep.
about perfect on timing.
Yeah.
I'm going to stop recording.